Welcome to the M-ary Aggregate Spread Pulse Modulation, or M-ASPM, as a physical layer modulation technique for use in low-power, wide-area networks, and in particular in LPWANs for IoT applications. But the first question is, why would we need another physical layer modulation technique when quite a few are already available? And why do we think that this one may be particularly suitable for use in LPWANs? Well, with a huge diversity and rapid growth of IoT uses, it may be very challenging to design a single LPWAN solution that would equally satisfy every need. And we often face such conditions when we must trade multiple physical layer parameters to meet conflicting technical requirements. For example, we would commonly trade the range for the data rate, or we may want to achieve resistance to both delay and Doppler spreads simultaneously. At the same time, we may want to trade as few things as possible. For example, we may want to have a network with the typical benefits of a non-cellular LPWANs, such as, say, long range and wide coverage, low cost of deployment and maintenance, and a long battery life, but improve its scalability and the quality of service. And M-ASPM offers lots of flexibility in implementing such various trade-offs. But before we discuss the ASPM's hows, let's see why we think that ASPM is suitable for LPWANs. Here is a plot of the spectral efficiencies versus energy per bit for several common modulations, including such prevailing in non-cellular LPWANs as Sigfox and LoRa. For LPWANs, we ultimately want to be somewhere in that shaded region on the left, where both the spectral efficiency and the energy per bit are low. In M-ASPM, by changing a couple of parameters, we access multiple values of spectral and energy per bit efficiencies within the shaded region in the middle. Note that it fully contains the LoRa's values, which is a good start. Further, this plot is for uncoded bit error rates. We can then use error correction coding to improve the effective energy per bit performance and to move the M-ASPM values towards the target region for LPWANs. So it looks promising as a suitable modulation technique for LPWANs. Now, let's take a closer look at the M-ary ASPM. First, a relatively low-rate information is encoded into a wideband designed digital pulse train. In such a train, only a relatively small fraction of samples has non-zero values, and each pulse can have m greater than or equal to 2 distinct states. These states can be the magnitudes and the arrival times of the pulses. For example, arrival times as remainders after division by the average interpulse interval. However, to keep the energy per bit low, we may not want to use the magnitudes of the pulses for encoding, but only their polarities and the arrival times, since those can be changed without changing the energy of the pulses. Then, the designed pulse train is filtered with pulse shaping filters. The goal is to create a low peakedness signal with desired temporal and spectral characteristics and suitable for modulating a carrier. In general, a pulse shaping filter would have a limited bandwidth and a large time bandwidth product, or TBP, and its autocorrelation function, or ACF, would have a small TBP. Next, this digital signal is converted to analog, used for modulating a carrier, and transmitted. In the receiver, the signal is demodulated and sampled. By using filters matched to the pulse shaping filters in the transmitter, this digital demodulated signal can then be converted into a high peakedness pulse train corresponding to the designed pulse train. Initially, for synchronization, the filtered output may need to be obtained at a full sampling rate. After that, To extract the encoded information, one can use the matched filters as decimation filters to sample only at the points corresponding to non-zero values in the designed pulse train. Note that if the pulse rate is low, ASPM is a spread spectrum technique, where a relatively low rate information is encoded into a wideband waveform. Here's a detailed example of an M-ary designed pulse train. Note that we use the Iverson bracket notation. It takes the value 1 if the statement between the double square brackets is true, and it takes the value 0 otherwise. Here, MP is the average interpulse interval in terms of the number of samples. For each jth pulse, MJ indicates the lag of KJ from the value JMP. Specifically, MJ is the remainder after division of KJ by MP plus 1. Also, here each pulse has an amplitude of plus or minus 1. Then each pulse has the number m of distinct states, which is equal to twice the average interpulse interval and can encode log 2m bits. Now, if this high peakedness train X hat is the input to a large TBP filter, G hat, then the output is a lower peakedness signal that is a piled up aggregate of these 3 time-shifted stretched pulses. This signal is band limited and its peakedness is low. It can now be converted to analog and used for modulating a carrier. In this example, the autocorrelation function of the filter is effectively a 3-point triangular pulse that can be viewed as a slightly broadened 1-point pulse. Then, if we filter the aggregate digital signal with the matched filter G, we'll obtain a pulse train consisting of 3 3-point triangular pulses that correspond to the pulses in our designed pulse train X hat. From this received signal, we can then obtain the arrival times and the polarities of the pulses in the designed train, that is, decode the information. And here's a particular example. In the designed pulse train, we use 8 distinct possible pulse locations relative to J and P. Then we can encode 3 bits per pulse for non-coherent detection and 4 bits per pulse for coherent detection. In this case, we also want the transmitted signal to occupy only a single sideband. To achieve this, for pulse shaping, we use 2 filters, G hat and H hat, which are the real and imaginary parts of a nonlinear chirp with the desired autocorrelation function having a small time bandwidth product. Thus, we create 2 spread pulse sequences. In addition, we want the transmitted signal to consist of constant envelope pulses. Thus, we use the filters that are short enough so the pulses don't overlap. Each of these sequences is then converted to analog and used for quadrature modulation of a carrier. In the receiver, we can use either non-coherent or coherent detection. Of course, particular demodulation techniques may vary, and here we use the 2 most straightforward. For the non-coherent detection, we use a quadrature amplitude demodulator to obtain the in-phase and quadrature components. Then we use the matched filters G and K as shown to obtain 8 samples per pulse of the high peakedness pulse train, shown in the box with the white background. This corresponds to the designed pulse train. Out of each 8 samples, the position of the sample with the largest magnitude will correspond to the position of the respective pulse in the designed train. The non-coherent detection does not require precise carrier synchronization, neither in phase nor frequency. But, as you can see, it does not recover the polarity of the pulses. Thus, we don't recover the most significant bit in the symbols encoded in the pulses of the designed train. For coherent detection, we would need to recover the phase of the carrier. But then we can also measure for each pulse the polarity of the sample with the largest amplitude, and thus obtain an extra bit per pulse. To encode more bits per pulse, we can add more possible time shifts for each pulse. This will reduce the energy per bit, but we would need to obtain respectively more samples to decode the information. So, what about the spectral and energy efficiencies of M-ASPM? Well, both depend to a large degree on pulse shaping. As far as the energy per bit performance, we first assess it for an additive white Gaussian noise channel as an initial benchmark. For fading channels, this performance will be affected by additional factors, such as particular shapes of the PSFs, relative spacing between the pulses in the design trained, and so on, and becomes more complex. In the paper, we show that for uncoded bit error rates in an additive white Gaussian noise channel, the energy per bit efficiency of the M-ASPM is the same as the LoRa modulation, with the spreading factor equal to log 2m for both coherent and non-coherent detection. To achieve the maximum spectral efficiency in M-ASPM, we can use PSFs with the ACF as a raised cosine filter with zero roll-off factor, that is, the sinc function. Then, the maximum uncoded spectral efficiency of M-ASPM is 4 log 2m over m for coherent detection, or 4 times that of coherent LoRa with the same m, and log 2m over m for non-coherent, or the same as non-coherent LoRa. What is different from LoRa is that in M-ASPM, the spectral efficiency is not constrained by the value of m, and is always inversely proportional to the average interpulse interval NP in the designed pulse train. Here, it's shown by the red and orange curves for the M-ASPM, with the factor of 2 difference in MP for any 2 adjacent same color curves. Thus, we can maintain the desired quality of service for any SNR at any given bandwidth and energy per bit by changing MP. For example, here, for 16 ASPM, we achieve the desired bit error rates at different SNRs for both coherent and non-coherent detection by adjusting the interpulse interval in the designed pulse train. In this plot, we also compare the calculated and the simulated BERs. On the right, we illustrate the PSFs used in the simulations and show the resulting power spectral densities, or PSDs, of the modulated carrier. As we consider using M-ASPM in LPWANs, we would also want to assess the multiple access capabilities of this modulation. For example, the main factor limiting scalability of LoRaWANs is co-spreading factor collisions. That is, collisions between 2 LoRa frames with the same spreading factor and frequency. This is a consequence of a relatively small number of different spreading factors employed by LoRaWAN. For example, a LoRa network with spreading factors ranging from 7 to 12 employs only 6 different spreading factors. In contrast, an M-ASPM network with a similar range of spectral efficiencies, and therefore covering a similar area, can utilize a much larger number of different PSFs, satisfying the quasi-orthogonality property when cross-correlations of different PSFs have large TBPs as illustrated here. This enables multiple access akin to asynchronous code division multiple access, or CDMA. As time on air increases, with the decrease in spectral efficiency, we'll have more inter-PSF collisions. However, it also becomes easier to design a larger number of quasi-orthogonal PSFs, even while effectively preserving the constant envelope property of transmitted pulses. At the same time, As illustrated here, the signal-to-interference margins increase with the decrease in spectral efficiency. This enables us to significantly improve the M-ASPM's network scalability by avoiding co-PSF collisions. To summarize, M-ASPM is well suited for IoT LPWANs. In addition, multiple trade-offs enabled by an M-ary ASPM may help us address a broader range of IoT applications, both static and mobile. Thank you for watching.